Good afternoon. My name is Alex Chen, Provost of the CTU. So it's my honor to introduce today's seminar speaker for this Institute of Advanced Study Distinguished Seminar Series. So our distinguished seminar speaker, Professor Chris, how do you pronounce last name? Matyjaszewski. Is that okay? Okay. So he's a J.C. Warner University professor of natural sciences, and I would like to just share with you some of his most famous work. Right? It's this atom transfer radical polymerization. Okay, have won him the great reputation all over the world, and he actually was nominated to be considered for a Nobel Prize, okay, because of this ATRP, the very clever solved methods, okay, and I don't really need to go through all the list, okay, to talk about all the distinguished awards he received so far, right? But then just give you something in perspective, okay. So, so he has more than 95 citations, okay, and actually index of 149 and more than 1,000 published papers, okay, right? So that gives you something to think about, not only the in-depth work, but then the breadth of the work, okay, from this is ATRP and also his work. So due to this great contribution, he has been actually elected as a National Academy of Engineering members, and also Polish Academy of Sciences, Russia Academy of Sciences, and also as a fellow of the National Academy of Inventory, and also IUPAC and the American Chemical Society. Okay, so with that very brief introduction, let's give a very warm welcome for.
Thank you very much for very kind words, and also for invitation to visit City University of Hong Kong. It is my second visit here, which I enjoy tremendously. And in fact, sometimes in China, they used to call me Lo Ma. So it is a bit easier than the Matyjaszewski, but you pronounce it in a very accurate way. So what I would like to tell you today is in fact something which is related to macromolecular engineering. So engineering, as always, starts with designing some materials for certain purpose, and then it is followed by very precise synthesis for the chemical part, and also processing in order to reach certain materials properties. But we'll be talking about molecular or macromolecular engineering, which is really polymer chemistry, more or less, preparation of polymers with very precisely controlled architectures. And we try to do that by using free radicals. And free radicals are generally very reactive species, very difficult to be controlled, whether it is in politics, they kill one another, they never listen to what you want them to be listened to, and in chemistry it's the same. So radicals terminate very fast. In fact, as fast as they meet, they would terminate, so with diffusion control rates. So typically what happens in a radical polymerization, the lifetime of a radical is roughly speaking 1 second. So during 1 second, you cannot do much chemical reactions because it is too short time to add second monomer, to add some other reagents. So you need to extend life of propagating chain from 1 second to hours. And we do that by equilibrating these active radicals, free radicals, with dormant species. And we do that in the presence of catalysts. So this is very special catalytic system because it involves both activator and deactivator. So two states of a catalyst are needed. And we, as you will see later, we borrowed some of the concepts from organic chemistry, but then we developed catalysts which are now 1 billion times more active than original catalysts. So one can use them at very low concentrations, at parts per million, but because radicals always terminate, you will convert irreversibly activator to deactivator, reaction would stop. So we need to regenerate this system, and I will show you some examples of using very mild reducing agents. And you can do something as simple as ascorbic acid, or sometimes sugars, but also external stimuli. You can use electrical current, light, sometimes even ultrasound or mechanical forces. But of course, it's not only important that you can make polymers, but what kind of polymers you can make. I will show you some examples of very special nanostructured materials. It may include some carrier particles, grafted nanotubes, or molecular brushes, but also some examples of bioconjugates, conjugates with proteins, but also with nucleic acids, and also some organic inorganic hybrid materials, so grafting from flat wafers, but also from curved surfaces, nanoparticles, nanotubes, and some others. And I should tell you that we are very happy that we work with many industrial companies. We have over 50 companies from all over the world, essentially, and we sign also 16 industrial licenses. I will show you some examples of applications of ATRP commercial polymers on some next slides. But let me start really how we started in organic chemistry. So if you look at the radical chemistry in organic chemistry, one of the first examples was presented by Karach nearly 80 years ago. So he took chloroform, and in the presence of some alkenes, vinyl monomer, if you wish, and light, there was insertion between hydrogen and carbon atom. And he did these reactions for maybe 20 years, and later Minishi in Italy, in 1961, took exactly the same chloroform, but he observed injection between chlorine and carbon atom. Totally different chemistry, same reagents. The only difference was that here, this was a glass flask, and here was a steel autoclave. So really what happens, nearly like with the Ziegler-Natta chemistry, there were some impurities, and in fact, this alkyl halide, which he took in the presence of iron, in that case, was reduced to radical. These species were oxidized to high oxidation state. A radical reacted with alkene, formed a product radical, much more reactive. He took this halogen atom back and produced a product. And the whole catalytic cycle repeated again and again. So a trick for organic chemists was to make only this adduct, one-to-one adduct. So they selected structure of compounds in such a way that substrate was much more reactive than product. So you could see here 3 chlorine atoms, carbomethoxy group. After addition, 1 chlorine atom and 1 carbomethoxy group. So this is approximately 100 times more active, which means that isolated yield of a product was 95% and spectroscopic 99%. You could see here that the amount of a catalyst was around 5 mol%, a lot. So what we wanted to do, we wanted to continue this process. And in fact, 20 years ago, when we described first time atom transfer radical polymerization and patented it at that time, we selected structure of the substrate, roughly speaking, the same as a product. So this one could go through the same catalytic cycle again and again and again, and the reaction was continuing and going on. So if you look really what happens with 20 some years ago, it was beginning of the controlled radical polymerization. In fact, you have to realize that radical polymerization is responsible for making, roughly speaking, 50% of all polymers in the world. This number, 100 million tons per year, is 100 billion kilograms per year. which means divided by 7 billion people, it is 1 kilo per month per average person in the world. So in Hong Kong, it would be probably 5 kilo per month or maybe even more. However, there is a problem with this process. Although it can be run in bulk, in solution, in water, in very large tolerance to many functionalities, that the life of propagating chain is only 1 second. So 1 second is too short to make block of polymers, sophisticated structures, so you cannot control polymeric architecture. No block of polymers, star polymers, and so on. So since that time, you could see it's a really explosive development of many papers, and on ATRP alone is more than 20,000 papers published, maybe half of all on a controlled radical processes. And because you are in China, you can check on Google that it would be, not in China, in Hong Kong, I'm sorry. In China, you cannot check that. But it will be around maybe 2 million now entries on atom transfer radical polymerization. There's also pretty large expectation in the industry. Bob Matson from DuPont estimates that it would be around $20 billion a year market. So it's like a 10% of all polymers made by radical means, but 10% not by volume, but 10% by market share. So no commodities, but high specialties, coatings, adhesives, lubricants, thermoplastic elastomers, cosmetics, nanocomposites, electronic materials, biomaterials, in general, some advanced materials. So let me come back and compare conventional and controlled radical polymerization. So, as I mentioned to you, they both work with the free radicals. But normally, in a conventional radical process, monomer reacts with the chain end with the frequency 1 millisecond. So after 1 second, after 1,000 milliseconds, there is a termination process. So always was a challenge, how you can extend this 1 second time to hours and days. So one concept which we introduced was that you can put this radical, active radical, from active to a dormant state by reaction with some kind of a counter-radical. And this counter-radical is a stable radical, which means you can buy it from Aldrich. You can use nitroxide if you want to use some kind of a bio-related system. You can think about vitamin B12 chemistry. So in that case, this would be cobalt porphyrin. And then you can make a cobalt-free organometallic species exactly like vitamin B12. But in all of these cases, you need one of these species per chain end. If you want to make a short chain, degree of polymerization 10, means it should be 10 mole% of cobalt porphyrin, very expensive. So we wanted to make something cheaper, maybe using something as simple as chlorine or bromine, but in that case, bond is so strong that you need to heat it to 300 degrees to have it labile enough. So what can be done in order to reduce activation energy from 70 to maybe 10 kilocalories per mole? You can use catalysis. So this catalytic system, as I mentioned to you before, is very special, meaning that you have a two forms of catalyst: activator, which would generate radicals, and also deactivator, which puts it back to a dormant state. Without activator, there would be no polymerization. Without deactivator, it will be uncontrolled radical polymerization. You need both. There's also another approach, which is based on the really degenerate transfer. You have this atom, iodine, or derivatives of tellurium, or bismuth, or ditio compound, which would degenerate the exchange between active and dormant species. You could see what is on the left side, right side is exactly the same. So key of control for all of this system is how many times you propagate before you deactivate, how many times you propagate before you exchange. And this would define degree of control. So saying otherwise, what I do in all of these systems, I take this 1 second life of propagating chain, and I chop it on 1,000 pieces, 1 millisecond each. And then I insert between every millisecond, let's say, 1 minute dormant state. So this 1 second is still 1,000 milliseconds plus 1,000 minutes, so it expands like accordion, essentially into a day, sometimes a week, sometimes even a month. If you want to compare it with a person's life, if for example, Professor Michael Chen, would be active for 1 day and dormant for 1 month. In that case, he will live not 100 years, but he will live 3,000 years, which I wish him, of course, to do. But it's impossible for him to make him dormant. He's too active, as every person in Hong Kong. Everybody is living very, very, very fast. So I told you that we develop more active catalysts. This is really one of the areas and targets of our research. So instead, like organic chemists who are using 5 mol%, we started to use 1 mol%, 0.1 mol%, and eventually 50 ppm, sometimes 20 ppm, sometimes even 1 part per million. So these systems work. If you have very active systems, they can exchange very fast. But I mentioned to you that radicals always terminate. If they terminate, you convert irreversibly activator to deactivator, the action stops at maybe 5% longer conversion. So how can you regenerate this activator? You can do that in the presence of mild reducing agent. So in that case, you have electron transfer process. You reduce copper 2 to copper 1 in the presence of, for example, sugars, phenols, ascorbic acid, vitamin C, piece of metal. You can use tin 2 octoate, which is FDA approved reagent. You can use radical initiator, AIDN, in small amounts. You can use copper 0. This works very, very nicely. However, every act of regeneration will form oxidized agent. So for example, tin 2 octoate is very benign, but after oxidation, you form much stronger Lewis acid, tin 4 compound, which is toxic. If you start from AIDN, you produce more alkyl halide, you generate new chains, you cannot make glucopolymer in a clean way. So can I avoid formation of this oxidized agent completely? How can I run this reaction without these byproducts? I mentioned to you, this is electron transfer reaction. So can I inject electron, not by chemical means, but for example, by plugging in battery to the system? So in that case, if I apply cathodic current, I reduce copper 2 to copper 1, and I start the reaction. But if I switch current, I go to anodic conditions, I oxidize copper 1 to copper 2 and stop the reaction. And according to Nernst equation, the applied potential should define ratio of copper 1 to copper 2, which means concentration of radicals, which means rate of the reaction. So we started like classical electrochemists. We have 3 electrodes, platinum working electrode, and then counter electrode separated by a mesh in order to prevent any byproducts going there, and also we use reference electrode. And then progressively, we switch to a simpler and simpler systems. For example, we replace this counter electrode platinum mesh with the aluminum wire. It acts as a sacrificial electrode. No more separation needed. Instead of a platinum here, we use now stainless steel or glassy carbon. And in fact, you don't need to use potential stuff, which costs $10,000, but you can use current generator for $100, or you can use AAA battery for $1. And all of this really works very nicely. So here's an example. If you look at this, one of the most active system, hexamethylated tren as a ligand, if you have sufficiently positive potential, there is no current flow, which means there is no reaction. But then, if I go to more and more negative potential, for example, negative 700 millivolts, in that case current flows, then I can start the reaction. And I can flip it on and off between 400 and 700, 400 nothing, 700 it stops, 400 stops, starts. I can climb to whatever conversion I want. And you could see that the boron masses very nicely increase with conversion, and the dispersities go to values like 1.05 in the best living polymerization. Entire monomass distribution moves cleanly to higher molecular weight. However, you have to be careful. If I go to more and more negative potential, you start really seeing a second peak. And then, if you look what happened really to the electrode, you start seeing that this platinum electrode gets shiny like a copper electrode, because copper gets deposited. So in that case, what happens, you really deposit copper on this electrode, and if I go to a more positive potential, I can strip this copper, and I get shiny platinum electrode again. So this is really very good news, because I can remove and replace copper. Under these conditions, polymerization essentially stops, because there is no more catalyst inside. But then I can put it back again, and if I go to the same potential, I get the same kinetics, same evolution of molecular weight, low dispersiveness. So you can remove something like probably 98% of copper from the system, and then you can recover 90%, depends how long you wait for this copper to come back from the electron. So this really gives me possibility of making temporal control of polymerization. So how can I control reaction externally? One approach, which I told you, is by electrical current. And I can do that in some sense by changing in time process. I can do it also in space. And I can have also other stimuli, like light, but also mechanical forces and some redox reactions as well. So in principle, if you have two different stimuli and two different catalytic systems, two different monomers, you can selectively activate one or the other one. And of course, the target is to make some advanced materials. So with light, you can do, in fact, two different approaches. You can activate dormant species, but also you can reduce copper 2 to copper 1 in the same way as I showed you before. So this is done in a very simple way using the LEDs in a flask, and it depends whether you use red light, blue light, or violet. They interact with catalysts in a different way. Red light is inefficient. This is blue, this is violet, this is sunlight. So simply by exposing that to a sunlight, this is a rooftop of Mellon Institute, you can put your flask, and during day it goes, during night it stops, goes, stops, and so on. So really what happens under these conditions, you excite copper 2 species in the presence of electron donor, it is reduced to copper 1 and activates the process. Because we are using very small amount of copper, once you stop irradiating, radicals terminate, copper 1 gets oxidized to copper 2, and the reaction stops. So it will be on-off, 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 on-off reaction. Sometimes for electronic materials, something which Professor Alex Jen is interested, maybe we can remove total copper. So how to do that? You can use also organic photocatalysts. So this is an example of the phenothiazine, which can be excited by light to a photoexcited state, which is extremely reducing. So these previous catalysts, they have a redox potentials around negative 300 volts. This one has negative 2 volts. And you have to realize that 59 millivolts is 1 decade of a catalyst activity. So this is like 10 to the power 20 times more reactive. So it gives an electron immediately, and then reduces alkyl halide to radical and corresponding halide anions. Of course, the lifetime of this species is very short. It is in a range of a picosecond, sometimes femtosecond. So it depends really on the lifetime of this species, how you can control this reaction. And what we do here, we really start with polyacrylonitrile first, and then we go to block copolymer with polymethacrylate, and you can see again pretty clean shift of a molecular weight. I will show you some examples of application of polyacrylonitrile a bit later. So what about really mechanical forces? It's easy to think about light. You can make also sometimes masks and do it in a 3-dimensional space. But how to approach with the mechanical forces and catalysis? So we look really at literature, and if you look at piezoelectric materials like barium titanate under ultrasound forms a potential, piezoelectric potential exceeding 1 volt. So you can split water under these conditions. And there was a paper early last year by using also barium titanate for ETRP, however with a very large amount of the catalyst, around 10,000 ppm, like this old classic ATRP. And it worked, but on the low molar masses, no temporal control, because it was so much catalyst, you couldn't stop it. So what we did, in fact, we reduced the amount of copper to 100 parts per million, and you could see that in that case, you apply ultrasound, it goes, you switch off, radicals terminate, copper 1 gets oxidized to copper 2, it stops, and then on-off reaction. Good control of molar masses, low dispersivity. But if you look really what happens in this system, you are using a very large amount of catalyst. In fact, it's around 5 to 8%. So the question is, can we go to lower amounts? We switch first to zinc oxide. Zinc oxide, in that case, is in the amount not 5 to 8%, but 0.038%, so 100 times less. And a similar effect, on-off, on-off, on-off. Good control of molar masses, low dispersivities. These are commercial zinc oxide nanoparticles, so they, although they are 18 nanometers, I believe, but they still aggregate. So it is not transparent system. So can we go to completely transparent system and potentially use light and ultrasound together? So this is one example of 5 nanometers zinc oxide nanoparticles. They are made at home, essentially using octylamine as a surfactant. And you are using also 100 times less. They are completely transparent. And you have a good kinetics, nice increase of molar masses, low dispersivities. So we wanted to extend this system to biological materials, working in water. And first reactions in water were really beautiful. But if something works, you always think, do you need all components? So I asked my student, what would happen without zinc oxide? Reactions was going exactly the same way. So what happens in water, you use the sonication bath, just normal ultrasound. Water is split into hydroxy radicals. Hydroxy radicals initiate polymerization, forms carbon-based radicals. They take this bromine atom from copper 2, reduce it to copper 1, and polymerization goes like before. So you don't need any piezoelectric materials. It's enough in water to have the ultrasound on-off, 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 and still good control of molar masses related to low dispersity, especially if you add a salt to this system. So let me summarize this part. When you work with ppm copper, it's enough to stop the regeneration process, to stop ATRP, which is very good for macroscopic control, but also for any kind of a temporal, potentially spatial control. You can use very small amount of the reducing agent to control this reaction. You can use external means like electricity, light, ultrasound, mechanochemical approach, and of course, chemicals can be organic, can be also, for example, inorganic. So sometimes people complain about the headache of drinking red wine. It's written here, contains sulfites. And usually people think that red wine is better or worse, maybe better for taste, worse because of sulfites and headaches, but in reality they contain 100 ppm of sulfites only. White wine, not Chinese white wine, but great white wine, 200 ppm. Sweet white wine, 400 ppm. Dry apricots, 1,500. And nobody complains of a headache after dry apricots. So it must be another reason. So red wine is okay, essentially. I put here this equation, which is really important, because it will tell you how dispersity or uniformity of change depends on concentration of the activator copper 2. I mentioned to you that control depends how many times you propagate before you deactivate. It depends on this rate coefficient and concentration of copper 2. If I go to lower and lower concentration of copper, 100 ppm, 50, 20, 1 ppm, I would like that all of this copper is in the form of copper 2 rather than copper 1. And this depends on equilibrium constant. If I have a large equilibrium constant, I have a larger fraction of copper 2. So what we want to do is really to use larger and larger equilibrium constants. This is one of the probably nicest correlations in radical chemistry. You could see this ATRP equilibrium as a function of the redox potential of copper species. So this spreads over 9 orders of magnitude. And by certain rules, if you want to use a certain ligand for copper, what you need to have more nitrogen atoms. 4 is better than 3 than 2. The bridge between nitrogen atoms, 2 carbons better than 3 than 2. Branch structure is better than cyclic and linear. Nature of the nitrogen atoms, alkylamine, pyridines, much better than imine or other amines. So these circled in red systems are really the best of the best. And they are more or less positioned here. So can I develop still more active catalysts? I have these principles, but I explored all of these possibilities. So idea which we have is that we can use sometimes electron-donating substituents on pyridines. And you have a commercial precursor of this material with dimethyl methoxypyridine. If we incorporate one of these arms, you go from TPMA to TPMA 1 star, you put 2 of them, 2 star, 3 of them, 3 star, by a factor of 10, 100, 1,000 times more active systems. And very recently, we published this year in JACS, you can have this dimethyl aminopyridine, which is additional 100 times more active. So activation and deactivations are both nearly diffusion control. So it is tremendously active catalyst. So in these catalysts, organic chemists can now borrow our ligands, like we borrowed from them originally, these BP systems, and you can use various reducing agents, including radical initiators, including sugars and ascorbic acid, tin compound, electrochemical approach, light approach, and instead of using this 10 mol%, you can use 10 parts per million, completely clean, clear reaction. So it would be important for organic synthesis, making pharmaceutical compounds, and so on. So let me come back to the idea of really controlling by macromolecular engineering materials. What kind of elements of molecular architecture we can do? On one side, for polymer, you can control composition. Not only making statistical copolymers, but making block copolymers, making statistical but also periodic structures, maybe sequence control, and then controlling gradients, continuous composition change along the chain. They have dramatically different mechanical properties, thermal properties, broad glass transition, behave in a different way. Instead of making linear chains, we can make rings, we can make stars, we can make humps, we can make gels, we can make hyperband structures. And you have to remember that radicals are very tolerant to functionalities. You can put hydroxy amino acidic group, you can put protein, you can put nucleic acid. They all are okay with radicals. And you can put these functionalities in many parts. And of course, you would like to combine them sometimes together. So making pom-pom-like structure, or this neutron star with 2 different arms, 2 different functionalities. Maybe excellent materials for solventless coatings, very low viscosity, very high cost linking eventually for automotive applications, or making molecular brushes. So if you look at these structures, they are all drawn by Photoshop or Adobe Illustrator, and you can do probably better than me. But how can you prove that you make them? So in that case, you need sometimes microscopy, maybe electron microscopy, maybe sometimes also atomic force microscopy. So here's an example of a molecular brush. We make them first by constructing a backbone, degree of polymerization 400. We start with the hydroxyethyl methacrylate, the same hema, polyhema which is used in contact lenses. Then we convert every hydroxy group to bromoester, and then grow these side chains. So this is a very special material because it's very soft. It's based on polybutyl acrylate. 95% of material is polybutyl acrylate. But it has a molar mass 2 million, sometimes even 10 million, sometimes 100 million. Side chains are extremely densely graphed. Graph density is 0.2 nanometers. So they really spread like in a bottle brush system, when you use this bottle brush for cleaning test tubes. But this is 100 nanometers bottle brush. If you compare it with a classical 10 centimeters real bottle brush, it would be like 10 centimeters from here to one job. So it's a really very tiny special material. I mentioned to you that they are very soft, they are liquid, although very high molecular weight. And if you put them, this liquid, on the graphite surface, you could see spreading them in a very uniform way. It's very important to understand, for example, lubrication phenomena for the even hard disk drives. So you have a plug-like diffusion, then you have diffusion between these chains, and sometimes even the rotation of a particular brush. Sometimes they can be trapped because you may have some defects on the surface, but it's very important that you can really control them individually, and this is of course accelerated. The whole frame is approximately 10 hours, but you see how these brushes move. They are sometimes also applied for the biomedical, potentially at least, biomedical area. So this is what happens in our joints. You have synovial fluid and you have aggregates, which a major component is a lubricant. So lubricant has these very soft, mucin-like domains with two parts of the amino-containing groups which connect to the hyaluronic acid. And we wanted to make a synthetic model of this lubricant by using methacrylate with phosphorylcholine functionality, very biocompatible, and also two parts of the ammonium groups, because this was done on a mica surface, so it can connect to mica surface. And also another example is for the hydrophobic brush as well. So here is really how you compare this natural lubricant with synthetic ones. If you have a larger slope, you have a larger friction. Here, you have a friction coefficient by a factor of 10 or even more lower. And this natural lubricant, at applied higher pressure, this normal force, just breaks. And this can survive to much larger values. If you take even this hydrophobic system, this is done in a DMSO as a solvent, you could see that this friction coefficient is like by about a factor of maybe 100 times lower. So they are practically frictionless materials. So this may have some applications in joints, essentially, after both hip and any kind of the arthroplasty. Here's another example of what you can do by connecting this brush with nucleic acids. So we start with the brush, which is water soluble, and when it contains bromine atom at the chain end, we replace in a very simple way with sodium azide, bromine is by azides, and then connect DNA with alkyne functionality to the brush. So you have now hundreds of these DNA bristles connected to the brush, and because it's negatively charged, you can intercalate this tetracationic yo-yo-1 dye with thousands of these fluorescent brushes. They're extremely bright. But also you can connect them to secondary, primary antibody to target particular cells. If you look at emission properties, this is the best on the market commercial quantum dot antibody material, and these are our brushes, which are roughly speaking 100 times brighter. But I wanted to show you something related to the mechanical properties of these brushes. They are very, very unusual. So if you take any material, polymeric material, below glass transition temperature, it is very hard. So when you think about the plexiglass or polystyrene, it has a modulus of stiffness around 1 gigapascal. And then if you go above glass transition temperature, this polymer starts flowing. And modulus of stiffness decreases. Then you have some kind of a rubbery plateau, and then system flows completely. You can process it by injection molding or some other techniques. So it's a rubbery-like state. But if you go to higher and higher molecular weight, this extends, or you can crossing it, and this is typical rubber. If you think about rubber band, it has a modulus approximately 100 kilopascal with this
10,000 times softer. But we wanted to make even softer material. So if I ask you what materials you know which are 100 times softer than rubber, typical answer is gels or hydrogels. So hydrogel is indeed 100 times softer than rubber with a modulus in a range of 1 kilopascal, but hydrogel is 99% water, 1% polymer chain. When water evaporates, hydrogel dries, becomes very hard. If you want to use hydrogels for contact lens, you must expose them constantly to saline solution. So can we make a material like hydrogel which would never dry? It would be one component material, never dry. How to design material like that? So we start with a network, which is really like a hydrogel, but we swell it in monomer and grow these short side chains. They cannot entangle, and in that case, they act as a diluent, which would never dry because these short side chains are connected permanently. So here is a really example how we do it. We start with a bottle brush backbone, degree of polymerization 2000, so they are roughly speaking half a micron long, sometimes up to a micron. And then we grow side chains from degree of polymerization 17, 23, 34 to 130. You see two phenomena. One is that these brushes become more and more separated, one from another, because a lot of side chains are lying in between. What you see here are dissolved side chains in fact. But the second is that you see them progressively getting more and more stretched. Because these side chains, they become longer, they want to go on a mica surface and stretch the backbone. What about mechanical properties? So we had this project for several years, collaborating with Sergei Sheiko at UNC, but also Michael Rubinstein and Andrei Dobrinin, and they came up with a very simple equation. These terminal modulus should scale with a power negative 1.5 from the length of the side chain. So this is prediction, this broken line, and these are experimental points. So this is polybutylacrylate a lot, million molecular weight. Like I told you, typical rubber would be in a range of 100 kilopascal. And then I had side chains 4, 17, 23, 34, 130. All on this line. But this one with 130 has a modulus 200 pascal. So it is not 100 times softer than rubber, it is 1,000 times softer than rubber, and it never dries. So two properties are important. One is really how soft, the other one how elastic. So this is an example of a hydrogel. This is 10% polymer network, 90% water. This is 8% backbone, 92% side chain. And you could see how dramatic difference in properties are. This is in fact very brittle, although it's 90% water. So there are a couple parameters which are important. One would be length of side chains. The other one is also graph density. If you graph too dense, they are having too much tension, they can also break. So we control this graph density, we control also cosmetic density to make them optimal. So you can make them, as I mentioned to you, in two ways. One is that I start with a network, dissolve it not in water, but in monomer, and go side chains. Not too long, because they will start entangling. So I start with the brushes, connect them together. But in fact, at Kaneka Corporation in Japan, they use even simpler approach. They make a monofunctional, difunctional cross-linkers. And in that case, you use very large amount of the diluent, small amount of cross-linker, to get, roughly speaking, similar material. So here's an example with a Japanese egg. So it is dropped from a height of maybe 1 meter, and this is a raw Japanese egg, as you see, and it survived. And if you are a little bit more ambitious, you can make a bigger challenge. You go on a third floor, drop this egg, and it survived more or less to the same degree. In fact, the biggest challenge is how you can center it, that it would not go at the top, because otherwise it would obviously fail. So they developed recently very interesting material which can be used for the transportation of fragile objects. So this is with a very small vibration isolators prepared by atom transfer radical process, and it's also acting as a shock absorbers. This is without, and you could see how it works with this isolator. You can quantify that also and look at the mechanical shaker. This is with, this is without, and if you look at the more or less same time, it's a really quite big difference. With steel bearings, it's more or less the same story, and you could see here the with isolator and without isolator. So the sample is dramatically different. There is also another less serious example. Small chickens in Japan of the size of this 5 yen coin. You could see here what happens if you have no vibration isolator. So all of these chickens are dead, essentially, after the 1 meter transportation. They don't look very bad. But if you look with vibration isolator, it is a very different story on the same surface, going more or less under the same conditions. So you have a really, this vibration isolator absorbs all of the shock coming from the rough surface. And somebody told me that maybe somebody glued them to the bottom, but you will see in a moment that this was not the case. So if I can continue a little bit with these biological systems, chickens as biological material, we can go also to molecularly biological systems. So this is an example of the bioconjugates. And this is area which really did not exist 10 years ago, because previously most people were conjugating polymers like pegylated structures onto proteins using very large excess of these corresponding packed structures. So if this is, let's say, 50,000, this is 50,000, you need to use maybe 50-fold excess of the polymer run under very low conditions. Very difficult to separate unreactive pegylated structure. Another approach is that you put functionality. For example, this is 123 positioning GFP protein. You add catalyst, you add monomer, and then you grow polymer chain, and by dialysis, remove all of the unreactive monomer and catalyst. You can do the same, in fact, with DNA. We put DNA on a machine, we edit phosphoramidite with bromoamide, and then we grow corresponding polymer out of it. You can grow in 2 parts, you can grow also in the middle from different parts, making polyplexes and others. So why do we do that? In fact, there is a big interest of using enzymes for pharmaceutical purpose, but also for protein therapies. And sometimes you would like to do that in organic solvents. So most proteins will be denatured, but if you grab them with the polymer chains, they are like armored, in some sense, enzymes. So they cannot denature, they cannot really be unfolded because these polymer chains keep them together. And you can think also about protein therapy. Typically, several protein therapies administered by the IV injection. Oral, you cannot do that because stomach pH is 1.5, and in that case, they would be denatured immediately. But if you cover them with the polymer chains, they can pass stomach, go to intestine, and get absorbed with the appropriate conditions. Analogous approach is really when we would use the organic inorganic hybrids. Instead of the natural products, we use inorganics. And this starts with putting functionality, for example, on a silica. So instead of silanol groups, we have now bromoesters. And then we grab polymer chains with a certain accuracy. We can do it from flat surfaces, from nanoparticles. We can start from the cylindrical, for example, mesoporous silica. It can be from outside, can be inside as well. And you can form very uniform structures. So this is one example of a photonic crystal-like material. Silica 200 nanometers, grafted with polymer. Normally colloidal crystals are very brittle. There is no cohesion force. But here, because you have polymer chains grafted, you can really stretch them, you can bend them, you can also look what happens under mechanical stress with the change of a color. So the classical Bragg diffraction depending on the distance and difference in refractive index. You can load sometimes as much glass as 78% or 75%. So this material is 75% glass, 25% polymer, but you can still stretch it and bend it and have a very good mechanical property. So I mentioned to you that we are also interested in the nanocarbons or electronic materials in general. So on one side, we start with these nanoparticles, we graft them with polyacrylonitrile, and then we graphitize the system to make polyacrylonitrile satellites, like graphitic structures. We then etch this silica, and then you have the one component highly porous porosity up to 1,000 square meters per gram systems. I mentioned also that we can use mesoporous silica, 10 nanometers, cylindrical openings, and then you can go polyacrylonitrile, graphitize, remove silica, and get these 10 nanometers replicas of the nitrogen-doped carbons. You can do the same, in fact, also using soft templates. So this is based on block copolymers. We are using typically polybutyl acrylate, polyacrylonitrile, and can have a lamellae, can have also cylinders and spheres, and you can play with the whole range of the morphologies. One of the most interesting, in fact, is the gyroidal system, because it's bicontinuous. And it is bicontinuous with a good connectivities on a distance of tens of microns or hundreds of microns even. So classical chemistry, which is used in the carbon fibers, you start with polyacrylonitrile, then in the presence of air, you stabilize it, and then graphitize it up to maybe 800 degrees. If you go to higher temperature, you lose nitrogen. And we need nitrogen for the, for example, electrocatalysis, for oxygen reduction, for hydrogen evolution, for supercapacitors, or even for carbon dioxide reversible absorption. So this can be done in a very efficient way, and also doping with nitrogen up to 12%, sometimes 14% nitrogen. Sometimes with sulfur as well. So I wanted to finish with some examples related to lithium batteries, because some of these carbon-based systems can act as the electrodes, but of course the challenge is how we can go from lithium-ion batteries to lithium metal batteries. In that case, you will have a much larger specific energy density and smaller size and lower weight and potentially much better systems. So typically, if you start with lithium metal batteries and if you have a combustible electrolyte, any kind of a damage gives fire. It can be used sometimes also to grow in a dendrite because they are very soft and these dendrites can really make a short. So what can we do with polymers in lithium metal batteries? On one side, you can do something with lithium anode, but this is practically not explored. I will show you one example later. Very important would be also an interface between the electrode and electrolyte, and how you can really reduce different side reactions and also mitigate volume change. Electrolytes is a very critical importance. And one example, and I will show you this example, is totally reversing the solid electrodes, cathode and anodes, and the liquid electrolytes, making solid electrolytes and liquid, for example, anodes. And then the same story is with the cathodes. So here's what happens if you start replacing liquid electrolyte with a solid. There are some materials like yttrium stabilized zirconia or garnet materials and some others which have a very good conductivity, but in this particular case of YSD, you have an oxygen vacancy on the outside. And in that case, they can absorb anions, so interact electrostatically with anions, and move lithium ions much faster. So first you have a transverse number approaching unity, and also much higher conductivity. So this is polyacrylonitrile alone. This is mixed system. This is from this paper. And now if you graft from this YSD polyacrylonitrile, you could see that conductivity is increased by more than 1 order of magnitude. So idea which we had was really that if we want to prevent this dendrite formation, can we, instead of a solid electrolyte, have or liquid electrolyte, have a solid electrolyte, and then this anode can be really composite materials based on the nanoscopic alkali metal particles. So we prep these alkali metal particles, lithium ions, and you could see this is 41% lithium metal in a polymer, and with the 5% of a carbon black, and this is how it performs. It's really size of these lithium nanoparticles. This is 50 microns, so it's a sub-micron system. So we tried to combine it together, and I wanted to finish with the example of a collaboration which we have with the ionic materials here. They are preparing some batteries. You could see that not only you can puncture, but you can cut it and you can put it later together. And if you connect it to the iPad, practically it gives you back again the all energy which is needed. And of course, another question would be, can we have a larger scale also grid system based on those lithium batteries? So the last part, I will have still 5 minutes or so. It would be example, what can you do really on a larger commercial scale with atom transfer radical process? So we published 10 years ago this book. Now it will be next year a second edition of this book on macromolecular engineering, which really relies on the back engineering, on design, preparation, and also processing of these materials in order to have a certain specific targeted functional properties. So if you are interested, you can have 4 volumes. One is really how to make it. Second, what to make, what kind of a molecular architecture, how to characterize and process it, and also what are particular applications. This would include some advanced materials, electronic materials, but also biomaterials, and some others. So our first really collaborator in this area was Kaneka in Japan, and they had this small pilot plant originally in Kashima, Japan. They do that in mostly for the sealants. So they are polybutyl acrylates, roughly speaking 10,000 molecular weight, with 2 functionalities which can be either UV curable or sometimes moisture curable. So these are examples of these sealants. And for comparison, this is classical silicon sealant. This is after 1 month, and this is after 4 years. So dramatically better behavior for several reasons. First, acrylate is polar, so it interacts with the mineral surface much better than non-polar PDMS. Much better functionality, and this is also leaching because silicon is really a kind of a maybe self-healing system, but also self-leaching system. It is more dynamic, and polybutyl acrylate, once cosmic, stays like that nearly forever. I think in Hong Kong, there are many high-rise buildings, so probably they are using these special sealants also. And one option is to use them also for self-cleaning windows. So self-cleaning window is really covered by a very thin layer of titanium dioxide, which acts as a photocatalyst to remove all organic impurities. And then rain really cleans that. But if you have inorganic impurity, it doesn't work. So this is PDMS sealant, and this is this Kaneka sealant, which is together with Saint-Gobain and Pinkerton. I think they are developing the whole package together. They also made something for automotive application. So if you look at the gaskets in the intake manifolds, this is what happens with PDMS. This is what happens with the acrylate-based system. Much more polar, gasoline vapor does not pass through. So 10 times less loss of gasoline vapors. Good for environment and also good for the energy performance. in PPG, they developed very special dispersant, also mostly for automotive, but also for appliances and some others. These are examples. They got the award 10 or 5 years ago for the best in dispersant used in aviation and also in the automotive application. But this is probably one of the most appealing examples. This is the Jeff Koons is a modern sculptor. He lives in Manhattan, and he sold this hanging heart for $23.7 million. This was the largest or highest ever bidding on the internet auction by a leading artist. And PPG said that he bought paint for $23 only. So PPG did not make much money, but Carnegie Mellon didn't make much money, but art is very important. Without art, nothing will happen. But at the same time, art is really only one person. It's me. It's whether it is Da Vinci, whether it is this guy or somebody else. Science is different. Science is we, because science we need really to work together. And for science, I think, like in your Institute of Advanced Materials, Advanced Systems, really requires both chemistry and biology and all interfaces with the electronics, medicine, and some others. So I think in your university and your institute, this is really what happens. So I wish that this will be continuing with a great success in the future. So I would like to acknowledge some people who did this work. This ultrasound was done, in fact, by an exchange student from Sichuan University who stayed for 1 year with me. The superactive catalyst by Tom Ribelli, with new lithium batteries by Sipei Li, who is from Zhejiang University. Electrochemistry was done by Marco Fantin, and photochemistry by Shangcheng Pan, who is now at Fudan University. And Ray did this polyacrylonitrile system is quite successful. So I would like to thank you for your attention and answer any questions you may have.
Now, thank you very much for very stimulating talk. Right? So first, I would like to open this forum to the audience. Anybody have any questions? Okay, Jimbo.
Oh, yes. Very nice talk. The piezoelectric nanoparticle catalysis, pretty interesting. In the general sense, the piezoelectric material would have a positive and negative surface. How that can affect the redox chemistry during the NVRP?
Yes, so in fact, the largest piezoelectric effect is for barium titanate. And in that case, it can really provide electrons on the surface. And this electron can be transferred to copper-2 to reduce copper-2 to copper-1 species.
Yes.
But this is not only potential itself, but also affinity of the catalyst to a surface. So, for example, zinc oxide has much lower piezoelectric effect, but better performance. And in that case, it may be specific interactions of this copper catalyst with the surface as well. We had one example of the barium titanate, which was grafted with polymer chains to disperse it better. And in fact, first, the effect was very poor because this catalyst could not approach the surface because of the highly grafted chains. But then if you continue sonication, it accelerates tremendously, probably because ultrasound can cleave some of these chains from the surface, make an open area, and then this catalyst can come, get reduced, and start the polymerization. So I think it's on one side would be piezoelectric potential, and especially if you have a negative charge or excess of electrons on a surface, which can jump on a copper-2 species and then reduce copper-2 to copper-1.
So you think if you have electron transfer, then so it should happen from the negative surface.
Yes.
Then you consider the positive surface is relatively inactive in this process.
I think so, but also you need to do something with these electrons later, right? So you need a balance, electrostatic balance. So if this is reduced, something has to be oxidized. And in fact, we use excess of the ligand, these amines, and these amines can form radical cations in order to balance everything together.
Good, thank you.
Bro. Yeah, I have actually two questions. The first one is beryllium titanate or the water splittings. What's the efficiency for the water splitting? And does the oxygen generation come along with it? Or?
This is really only citation from literature.
Okay.
When we seen that something like that happened, we were just inspired that one can really use the concept, but we never did any experiment ourselves. So this was really a reference, and I didn't follow what efficiency was. So I'm sorry that I cannot provide more details.
I got one more question on your ATRP reactions.
Mhm.
I saw that the reaction constant is in the order 10 to the 7th per mole per second.
Mhm.
So once we have microseconds, and I don't know how to convert it, how many molecules can be generated, because
Yeah, so many of these reactions are bimolecular reactions. So this is rate of a bimolecular reaction defined in concentration mole per liter per
Yes.
second.
yes.
So bimolecular reactions cannot happen faster than diffusion control process.
Okay.
So diffusion control process depends on viscosity. Typically, in a very low viscosity media, would be in a range of 10 to power 9
Okay.
mole per liter minus 1 second minus 1. And if viscosity increases, in that case, this diffusion control limit drops to 10 to power 8, sometimes 10 to power 7. So this is really, for polymerization, depends also on the mobility of chains. So for bimolecular process between two polymer chains, radical termination, sometimes if you go to gel-like structure, maybe 10 to power 6, 5, or 4. So for example, if you make a plexiglass, you may smell a little bit of the metal metacrillate, although it's already a glass. Meaning the chains cannot move because they are trapped in a glass state completely. But if you have a small molecule reacting with polymer chains, in that case, this diffusion control limit is smaller because although polymer chain is immobilized, but this small molecule can come very fast, whether it would be a monomer or it would be the activator. But eventually, if you cross certain viscosity or glass state, in that case, this reaction slows down. So for all of these systems, for control, it's really how many times you propagate before you deactivate.
Yeah.
So this is always, because it's a bimolecular reaction, it will be a question of concentration of the activator, so we cannot go below 1 part per million moles. Because even if reactivity would be much higher, they cannot diffuse fast enough.
Okay. Thank you.
Well, very fascinating lecture. In fact, at the time I'm coming, I thought you were talking about how to carry out the free radical polymerization. However, after listening to your presentation, it seems to me you already go beyond that level and talking about the material application. And you have been talking about the application as a vibration isolator and in the biological system and for the lithium-ion battery and so on. I just wondering, can you apply your polymer to the optoelectronic material, for example, in addition to the connecting to the quantum dot, right? And what I mean is, can you do something in that area? Make the, for example, some of the light emitting species incorporate some of the light emitting component into your polymer system, not the quantum dot.
I can see that Provost is smiling in a very positive way. So, I think that these reactions rely on vinyl monomers.
Mm-hmm.
So we must have a vinyl functionality, typically styrene, but also acrylate or methacrylate or acrylonitrile. So it means that we cannot have
any kind of highly conjugated systems in a main chain, but we can have them in a side chain. So if you would really immobilize some optoelectronic materials or attach them to the acrylate or metacrylate functionality, you can potentially polymerize a backbone, and then you will have these side chains of corresponding properties. You have, however, to realize what potential side reactions you may have. I mentioned to you that all of these systems are also dependent on a redox potential. So you can reduce not only catalysts, oxidize, but potentially also radicals. Radicals had a redox potential for acrylates around negative 600 millivolts, but for styrene negative 1 volt, which means you open window much more. But it will be always possibility that this electron transfer may happen. And even if you pass radicals, you have also monomers. Monomers can be also reduced. So some systems which are very delocalized, you have to look what is their redox properties, both reduction and oxidation, and are you in a window which you can really operate with.
Yeah, thank you.
Do we have any question from the students? Okay.
Would your group by any chance test these materials in amorphous metal? Like I saw a lot of application with just in, I saw the glass, the silicon-based glass, but we saw a lot of problems in like balance the base of the scale of the metallic glass research. So do you group by any chance do the material test in metallic glass and take the grain picture? Because there's no grain or some balance in like macro or prog scale metallic glass. Or maybe if you can do that, we can take further research into that amorphous status of the metallic.
Yeah, we haven't done exactly this, but maybe I can answer with another quite interesting system. So we were interested, in fact, in liquid metals.
Liquid metal.
Yes. So typically when you think about liquid metal is mercury. Mercury is very toxic. So we were thinking about some liquid metals, mostly for soft robotics, of a high conductivity and really liquid-like properties. So one example is eutectic gallium-indium alloy. So gallium-indium alloy at certain ratio has a melting point at plus 15 degrees. And then you can really disperse this alloy with initiator and start grafting polymer chains, making particles of the size of maybe 100 nanometers. And surprisingly, if you cool it down from room temperature, they start crystallizing at minus 80 degrees. Not plus 15, but minus 80 degrees. And then when you heat them up, they melt at minus 20 degrees. So you really change the range of this melting. Instead of a plus 15, you go minus 80 supercooling and then minus 20 recrystallization. So it's a really possibility of working also not only with solids, but with liquids in some sense.
So can I like understanding this way that this polymer into the just for now the liquid metal, it changed the crystalline process of the metal.
because really you are going to nano-dimensions, so they cannot crystallize. This nucleation process for crystallization is very much delayed. And of course, this liquid metal has a surface of a little nanolayer or monolayer of the oxide. So you attach to this oxide, you attach your polymeric initiator, and then it will change from that.
Any other questions? So I have one question, right? So I talked about a lot of things related to some biocompatible materials, right? So I don't know about you, right? But when I start to get older, my knees really fit, right? Okay, so sometimes I really need some lubricant. But is there any possibility? Can you say take bio precursor, either monomer or oligomer, right? So I can just inject it into my knee, right? And then just use an ultrasound to really do the recombination to sort of create some lubricant in my knees.
So there are really two approaches. One therapy now is that people inject hyaluronic acid, and it works, I don't know for yogis, but I had some colleagues, they say for 2 weeks it works, and then it doesn't. Because hyaluronic acid is degraded by some enzymes, threonase and they are gone. So one example which I showed you with these brushes. These brushes, they are based on phosphorylcholine, which is biocompatible materials. And we started doing that, of course, in vitro, and first it was on this mica surface. There are now some studies on the biocompatibility. We would not like them to degrade too fast because you would like to have maybe one injection only. And we start with animal studies. First was done with mouse, and then next one was dogs. And I think it is possible that it will be done in human systems maybe in a couple of years, because I mean you cannot go too fast. So there are really two questions. One is it enough to have just brush? This brush would act as a lubricant. We sometimes graft also from flat surfaces. In that case, it was Jacob Klein from Weizmann Institute who made an experiment. He had a 1,000 kilograms load, and with a force of 1 gram, he could just push it on top of the other one. The reason is that if you have a very dense polymer brush, they can not interpenetrate, they cannot entangle, they slide one on top of the other one. This phosphorylcholine has additional advantage that it is also highly water swallowable, like a ionic system.
Yeah.
So we have additional lubrication from aqueous system. And then it's a question how they can stay in your joint and not go somewhere else. So if we would have potentially some cross-linkable system, these side chains, potentially with glycidyl, epoxy group.
Grew on our bone.
Yes.
Yeah. Very stimulating, right? So, if we don't have further questions, please join me to really thank Professor Matyjaszewski, okay, for his very inspiring and wonderful talk. Thank you.